Hello, my dear students. I am B S Pandey, your physics lecturer. We are in lectures of standard 12. Today we will be in lecture number 70 and we will start the combination of inductor and RC circuit under voltage supply, and few more concepts today we will study. Hopefully we will start the mutual induction as well. So let me start today's lecture, my dear students. It is lecture number 70 today. Chapter 6 of NCERT, Electromagnetic Induction. Okay. So we are going to start today the combination of inductors. Combination of inductors. Okay. Here our aim is to find the equivalent inductance. If we are using two or more than two inductors simultaneously, then can we arrange one inductor behalf of that multiple inductors? This is our aim. Okay. So here the two inductor we are connecting in series. First we are going to start series combination. Alright, suppose the inductance it is L1 and L2. These are two connected with the source of battery. It is EMF E. Okay, here the current I will start flow and the current will be same in both the inductor. Why? Because the two inductors are connected in series. Current will be same for both inductor. Alright, now suppose the EMF drops or the back EMF produced by this inductor as E1 and the E2. Actually this total EMF produced, suppose it is at any state, it is T, then we can write here that E is equals to E1 plus E2. My dear students, if we could arrange one inductor behalf of these two inductors, then what will happen? The total EMF will be compensated by this inductor only. Suppose the inductance it is L equivalent. Here the EMF, the same current. This inductor will also draw from the battery, the source. Here we can write for all the inductors one by one. For this inductor L1, remember we are doing the operations same as we have done in resistors and capacitor. Okay, equivalent capacitance, equivalent resistance we have studied. In similar way we are doing here also. For L1 we can write E1 it is minus L1 di by dt, and for L2 we can write E2 is equals to minus L2 di by dt, and for this inductor L equivalent, what we can write? E minus L equivalent L di by dt. Bear in mind all the inductors having the same rate of change because the current is same. So for the same time all the inductor will experience the same change. Alright, same rate change. Now using this equation, if we will put the values in this equation, what we'll get? We will get that this E induced, that is the net EMF, minus L di by dt, which is minus L1 di by dt minus L2 di by dt. You can see all the quantities are common. Here di by dt will be cancelled out, minus will be cancelled out. So L equivalent, it will be L1 plus L2. This is the similar like the resistance. Na? Yes, if you are having the 2 Henry and 3 Henry are connected, remember inductor also having no any terminals, positive and negative. You can connect any, okay, if in any way, if you are connecting this inductor, if you will flip this inductor, there will be no change in the answer. It will be remain L1 plus L2, because this is the inertia, this is the property at the resistance, okay, at the mass. All right, yes, so the L equivalent will be L1 plus L2. Actually we used to give the negative sign, that is the back EMF, and that negative sign it is used for the EMF, not for the inductance. Okay, now so L equivalent will be L1 plus L2. Now the parallel combination, the second one. Okay, the parallel combination, we will connect two inductors in parallel. Here in this combination, we will take the two inductors in parallel. And we will connect with the battery. The EMF of two battery, here the inductance L1 and L2. Now look at here. In this parallel combination, if this is the L1 and L2, we have arranged here one inductor with the same source. It is L equivalent, leaving the current I. What will happen here? The current I drawn by the cell divide into two current. It is I1 and I2. Alright, now actually this current I divided into I1 plus I2, okay. Now for each inductor one by one we can write. For L1, what we can write? E1, here the EMF remains same in parallel. So this is the EMF. For L1, E will be minus L1 di1 by dt. Time remains same for both the inductor. For L2, it will be E equals to minus L2 di2 by dt. Yes. And for inductor L equivalent, it will be E is equals to minus L equivalent di by dt. Alright, now here we can write the values of I1, I2 and I3 in this equation. If we will try to find out if we will differentiate with respect to time, what we will get? Di by dt, it is equals to di1 by dt plus di2 by dt. Okay, now we are going to put all these values here in this equation. di1 by dt we can write minus E by L1. Okay, here di by dt we can write minus E by L equivalent, minus E by L equivalent. For di by dt we can write minus E by L1. E by L1 and minus E by L2 for the second inductor we can write. So this will be the common, taken at the common, cancel out, we will have the net result 1 by L equivalent, it is 1 by L1 plus 1 by L2 or 1 by L equivalent as L1 L2 L1 plus L2, and the L equivalent we can write L1 L2 by L1 plus L2. Okay, so this is the equivalent equivalent self inductance when we connect two inductors in parallel. Okay student, now we are going to solve few questions of LR circuit under DC supply. Okay, LR circuit under DC supply. You will study the LR circuit under AC supply also, and that you have to study in next chapter, that is the alternating current. Here in this chapter we are going to study the LR circuit under DC supply. Okay, yes, my dear student, try to recall actually what I told you earlier. If this is the inductor, connected with a DC source, current is I. If this current is moving in this direction, increasing, what will be the direction of induced EMF? Right now we will see that how this current will increase or decrease by the variable battery. Okay, inductance it is L. So the back EMF will be in this direction. If the current is increasing, this one, then back EMF will be in this direction. What you have to suppose, listen carefully, although I have explained already, again I am telling you, if this is the inductor and current I is increasing in this direction, then you have to consider a cell behalf of this inductor. This inductor will be considered as the cell, but you need two terminals where will be positive and which will be negative, which will be at high potential and which will be at low potential. Suppose this is the point P and this is the point Q. If I am telling you that current is increasing in this direction, tell me which point will be at high potential at the induced EMF. The back, due to back EMF, which point will be at high potential? So the answer will be, if the current is increasing, of course we have to put the battery positive terminal left and right. The right will be the negative terminal. Remember, there is no battery. We have supposed a battery due to the induced EMF, that is the back EMF. Okay, my dear students, due to the back EMF or induced EMF. Now, according to this one, you can say this P will be at high potential and this Q will be at low potential. Of course, P is at high potential and Q is at low potential because the back EMF will be in this direction. Alright, now how we have to solve the question? Actually, if you will write the questions, suppose I am giving you a very simple example. This is the inductor through which current is flowing certain value. Suppose the I, it is flowing 10 ampere, but this current is changing with the rate di by dt. It is given 2 ampere per second, and the inductance of this inductor, it is given L is equals to, suppose 3 Henry. This is the point P and Q, and I am telling you, represent the back EMF over here with the cell. You have to represent here a cell and you have to give the value of that cell, that is the back EMF. Then how you will solve this question? So you will solve this question like this way. First, here due to by this given value, you can see it is quite clear. This is positive and this positive is representing the current is increasing. Every 2 seconds the current becomes 2 ampere more. Okay, it is increasing by 2 ampere per second. Now, here we are going to represent a battery. As the current is increasing, of course, the back EMF will be in this direction. So this will be the cell due to induced EMF, that is the back EMF. Now what will be the value? So the value will be L di by dt, very simple, and it is L given 3 times L di by dt, it is given 2, so it is 6 volt. Answer, this is the 6 volt. Okay, now in this way, my dear students, try to solve this question. Another very simple question. A resistance is connected. Okay, here between point P and Q, you have to write the potential, that is VPQ. I am asking will be what? What is given? The current at an instant, it is given 5 ampere, and di by dt, it is also given, suppose 1 by 2 ampere per second, and the L it is given 1 Henry, R it is given 5 ohm. Okay, if you can solve, try to solve this question. What will be VPQ? You have to find potential between these 2 points. Okay, try to solve this question. Pause the video and try to solve this question. Okay, let me solve. If you have solved, kindly check and verify. I am solving here. So, student, first we will try to put a cell over here. The current is increasing, of course it will be the positive and it will be the negative. Once again I am explaining, my dear students, why I am taking here the positive and here negative. Once again I am explaining. Here the current is increasing in this direction, so the EMF will be induced to oppose the current, and if EMF induced in this direction, so we know that from positive terminal EMF, it is the current moves, so the positive terminal will be left side and right side will be the negative terminal. Okay, and it is due to the back EMF. Yes. Now, if we have converted, this is the inductor, already we are having a resistance over here. This is our point P and this is our point Q. How much current reached to this 5 ohm resistor? It is 5 ampere. Alright. Now, what will be the back EMF over here? So, it will be E equals to L di by dt. How much L? It is 1. And di by dt, how much? It is 1 by 2. How much voltage over here for the resistor? It is the I times R. So, I it is 5. And R it is already 5. So, the 25 volt over here and half volt over here. Now, it's time to write the equation, proper equation. VPQ, we are going and we have discussed what we have discussed in Kirchhoff's law. To write the proper sign, the same we will use. If we are moving here, the current is moving in this direction, we reach to the positive terminal, so the voltage will be positive over here. It is the plus 1 by 2. Now, in the direction of current we are going, so it will be the plus, and how much potential here? 25. So, it will be 25 and half. We can write, it is the 51 by 2 volt. Okay, my dear student. Now, one more question I am giving you. Try to solve. Very little bit I will change the face of that question. It is the resistance. Another inductor. Okay, one more resistor. Here the current, it is 2 ampere, and di by dt, it is 1 ampere per second, 3 ohm, 2 ohm, and L equals to 2 Henry. This is the point P, this is the point Q. Now you have to find VPQ. What will be the potential between these 2 points? Try to solve by yourself, my dear students. Then after I will solve, and then you will check whether you have solved correctly or not. First, try to give the polarity to the inductor. Okay. All right. Now let me solve this question. Here, the battery, as the current is increasing again. Okay. If you have solved, then good. Now I am changing the data. Try to solve another question. You will get the maximum question for your practice. Now I am changing the data. It is minus 2 ampere per second. Now try to solve. Again pause the video and try to solve for this value. Okay. Now let me solve. Because all the questions were looking very similar, I have been changed a little bit how to solve this question. Look at here carefully, my dear student. Here current is decreasing now. This value representing current is decreasing. So in this inductor, negative sign will be in this side and positive sign will be in this side. This will be the polarity, minus and plus. Okay. Now we have to write here the equation VPQ. It is the voltage over here, it will be the 2 into 3, that is IR, I into R, 6 volt. Now in direction we are going, here the minus we meet the negative terminal, so the minus L, and di by dt it is 2, so it is 2. Again we are going with the current, so here the 2 ampere current flows to this resistor, and 2 into 2. So the total, the value it becomes how much? It is 4 and 4, 6 volt. One homework I am giving you, my dear student. The 2 homework I am giving you. Try to solve. I, it is 3 ampere, L 2 Henry, L1, L2 it is 3 Henry, here the 2 ohm, 3 ohm, and di by dt it is minus 1 by 2 ampere per second. You have to find VPQ again. Okay. Now next homework, the second homework. Second homework is this one. The point P, point Q, 2 ohm, 2 Henry, 5 volt, 3 ohm. Current it is I equals to 1 ampere, and di by dt it is minus 1 ampere per second. Find VPQ. Okay, the 2 questions. I hope you are very clear about this 2 questions. You have to find potential between these 2 points. Okay. So my dear students, this is the LR circuit that we have studied under DC supply, direct current. The same circuit we will study in alternating current also, AC chapter also. Okay. So this is the questions regarding the potential due to inductor at the two terminal of the inductor under DC supply. Now the next topic we will study, it is mutual induction. In this lecture number 70, we will start mutual induction, and then we will study the coefficient of mutual inductance. Okay, as we have studied the self-induction, it is the back EMF induced in the same coil in which the current is changing and flux linked with the same coil. One coil, that is the single coil, changes the magnetic flux, and the same coil experience that change and back EMF produced. That was the self-inductance. Here mutual inductance, we will have the two coil. One coil will change the current, and due to that change in current, magnetic field will change. That magnetic field lines linked with the another coil, and that another coil will experience change in magnetic flux and start inducing an EMF, that is the back EMF, and this phenomena will be considered as mutual inductance. Mutual, it means the dependence of any quantities of one coil due to the change in quantities or the phenomenon in other coil. So you can write the definition of mutual inductance, my dear student. The mutual induction the phenomena of inducing EMF in one coil due to change in magnetic flux due to change in current, that is change in magnetic field, by another coil. Okay, this is called the mutual induction. Look at here with the pictorial explanation. Try to understand mutual induction. In next lecture we will continue this particular topic and we will calculate what will be the coefficient, with what inertia one coil opposes the change in flux in itself. We will calculate, but here try to understand this particular concept, mutual induction. Suppose, my dear student, we are having a coil. This one, let me draw a little bit bigger one. Okay, and there are the n number of turns in this coil. Suppose the number of turning, it is n1, and we have placed another coil, a smaller coil. Okay, concentric. These two are the concentric. Here the current is flowing in this coil, suppose I1. Okay, this is the axial line. This is the axial line. What we will write, my dear student, as the current is developed in this coil, if this coil having the radius r and this particular coil having the radius small r, what will happen? This coil will produce magnetic field. Am I right? Yes, of course it will produce some magnetic field, and the area of magnetic field will be entire this region of bigger coil. Yes, but how much flux will be linked with the second coil, that is the red coil? The flux linked with this red coil, it will be the flux linked with this coil, it will be the magnetic field which is uniform, we suppose uniform within this region, but area is not total area as much this coil. Area will be of this coil only, and this area, it is the pi r square. Pi r square. If you will multiply this area with the magnetic field produced by this coil, if this coil is producing magnetic field at the center that we used to study the uniform, suppose this coil is very small, so that it gaining the uniform magnetic field. Alright, so the magnetic field multiplied by the area of this coil will give you the flux linked with this coil that we have studied. And this magnetic field, suppose B, how much magnetic field will be produced by this coil, you can find out. Okay, and how you will find the flux, this is also very familiar, not very tough. Okay, this is the one case we are changing the current I. Here the magnetic flux linked with this coil, and if this current will change, the magnetic flux will change, and an EMF induced in this coil will give you the calculation of mutual inductance. Okay, this is the one case. The second case, suppose we are not changing the current in this coil, the bigger coil. What will happen if we'll put the current in the smaller coil? Okay, the smaller coil, then how you will calculate the mutual induction? Now the mutual induction and the mutual inductance now will be considered for the bigger coil. Now this is very important, and the very first our primary work to find the flux linked with this bigger coil. In what region magnetic field produced? The magnetic field actually produced in this hashed portion only. Remember, not in entire region of the bigger coil, only in the region of the smaller coil that I have been represented by this hashed. Okay, and then the flux will be same as the flux linked by this coil, because we cannot use the area of this bigger coil to find the flux linked by this one. Why? Because of course the area is this one, pi capital R square, but this entire coil is not getting the field lines. This much only it is the field lines. So the area will be of this much only, and this will be the flux linked with this bigger coil. So the flux remain same. It is, if the same current we are giving, all right, the same current we have given, or we suppose the same magnetic field, then in that case the the flux remain same. But there are number of factors. If you will change the radius, if you are changing, you can see the radius is smaller, the same current will produce the higher the magnetic field. All the things that we will discuss. Now the second case of mutual induction that we have to study in our syllabus, this is the question of NCERT. Remember, in examination you will be asked to find the mathematical expression for the mutual inductance of solenoid. If one solenoid is kept inside another solenoid, then what will be the mutual inductance? As we know that if a solenoid is kept inside that solenoid, another solenoid will be kept. Due to change in magnetic flux, inside the magnetic field will change, the magnetic flux will change, and back EMF will be produced in the other solenoid. Okay, in same way we will study. But today actually I have given only the introduction of this topic. It is the mutual induction. Again I am telling you, mutual induction is the phenomena of inducing EMF, that is the back EMF, in one coil due to change in magnetic field or change in current. That would be the better if you write change in current. Okay, it is the phenomena of inducing back EMF in one coil due to change in current in other coil. This is the mutual induction that we will study in next lecture. Okay, my dear students, thank you very much for today's lecture, students. Thank you very much.